Welcome to a journey through the heart of modern industry, where raw materials are transformed into the building blocks of our world. From towering steel structures to precision-engineered motors, these processes showcase human ingenuity and technological prowess. As you watch, consider, how do these advancements shape our lives, and at what cost to our planet? Let's begin with the fiery world of steel production. Med Steel operates the only integrated steel production facility in Kurdistan, covering nearly a quarter of a square mile. The production process begins with melting scrap metal in electric arc furnaces to produce molten steel. The steel is then cast into billets using continuous casting technology. These billets are reheated and passed through a bar mill for hot rolling into rebars and profiles, including angle, flat, square, T-shaped, and U-shaped. Advanced automation ensures precision and efficiency. A 52 megawatts in-house power plant fuels the entire operation, supporting sustainability. MedSteel combines modern technology and strict quality control to deliver high-grade steel products. Imagine the energy required. Does this efficiency outweigh the environmental toll? This robust process sets the stage for steel shaping elsewhere, like in Nepal. In Nepal, KN Engineering heats billets to 1,200 degrees Celsius on the pusher-type reheating furnace. The red-hot billets exit the furnace and pass through a descaling box before entering the rolling mill. The material undergoes progressive reduction through roughing, intermediate, and finishing mill stands. Each stand consists of heavy-duty gearboxes and precisely aligned rollers to ensure dimensional accuracy. A high-speed flying shear is used to cut the bars to predetermined lengths while still hot. The hot bars are then transferred to a cooling bed, where they are naturally cooled in an aligned and controlled manner. After cooling, the bars are straightened, cut to final commercial lengths using cold shears, and automatically bundled for dispatch. The plant is fully integrated with automated material handling and control systems. It is designed to produce 40,000 TPA of light and medium steel sections with consistent quality. Could automation here reduce human labor risks, or does it displace skilled workers? Across borders, similar techniques create versatile steel products. In Rebar, India, billets are rolled into flat strips. After reheating, the billets are descaled and passed through roughing and finishing stands. The continuous rolling shapes the steel into the desired thickness and width. Finally, the strips are cooled on run-out tables and cut to length for dispatch. Steel's journey often begins with casting, a craft blending tradition and technology. At Simplecomp Gießerei, 160 tons of molten metal are poured into molds in a casting pit. The production process begins with preparing the casting pit, where the mold is positioned and secured. Simultaneously, molten metal is prepared at the furnace platform, where raw materials are melted in high-capacity furnaces. Once the metal reaches the required temperature, large ladles are positioned and filled with the liquid metal. These ladles are then transferred using cranes to the pouring station. At the casting setup area, the mold is carefully closed and aligned. The pouring process follows, during which approximately 160 tons of molten metal are steadily poured into the mold cavity. Precision and coordination are crucial to ensure uniform filling and to avoid defects. After the casting is completed, the cooling phase begins, allowing the metal to solidify and form the final component shape. This marks the end of the casting process before post-processing operations begin. After several weeks of controlled cooling, the 136-ton cast component is carefully removed from the deep casting pit using heavy lifting equipment. It is then horizontally transported through the foundry to the cleaning area, a complex task requiring precise coordination between skilled personnel and automated logistics systems. In the cleaning section, the component undergoes mechanical cleaning to remove all remaining sand, scale, and casting residues. Once cleaned, it is subjected to thorough visual and dimensional inspection. The Quality Control Department then documents all results, ensuring the component meets strict technical and safety standards before being approved for delivery to the customer. Hand molding, melting, pouring, cooling, shakeout, blasting, measuring, recycling, reusing materials, minimizing waste, conserving energy, ensuring safety. In the AFWL 110 cable shielding line, the forming and welding process begins with precise feeding and alignment of metallic. The SLT 400 to 0 degrees laser cross welding system performs fully automated cutting, positioning, and butt welding of tapes with thicknesses from 0.05 millimeters to 3.00 millimeters and widths up to 400 millimeters. Using high-power fiber lasers, 500W, 1500W, it achieves narrow, deep penetration welds without filler material. After welding, the tape continues into the forming section, where it is shaped into a cylindrical, completing the shielding layer before further processing or insulation. At Procast Keel Foundry, the manual casting process involves skilled workers handling molten metal with precision. After being melted in an induction furnace, the glowing iron is transferred into handheld ladles suspended from an overhead crane. Workers carefully guide the ladles to the pre-prepared molds, ensuring steady and accurate pouring. Each mold is matched to specific component requirements, allowing for diverse part production. The controlled flow of metal into the molds is critical for ensuring casting quality and structural integrity. This hands-on process highlights the craftsmanship and expertise required to transform molten metal into solid. The process begins with the worker assembling the casting mold, followed by the sand being dried in a drum dryer, heated by a combustion chamber and burner. The worker pours the dry sand into the mold. The upper cylinder block mold is formed, then assembled in the casting chamber. Molten aluminum is fed from below at low pressure, completely filling the mold cavity. After solidification, the casting is removed and the excess material is discharged. During this process, exhaust fans and cyclone dust separators extract and filter airborne particles to maintain a clean environment. Dry product conveyors transport the used sand or leftover castings for reuse or disposal. This controlled low-pressure sand casting method ensures high-dimensional accuracy and surface finish for the engine's upper cylinder block. The investment casting process begins with engineers developing a suitable tool based on order drawings or 3D data. In the wax room, aluminum or steel injection tools are used to produce wax parts, which are assembled into tree clusters. These are repeatedly dipped in ceramic slurry and coated with sand about 10 times to form a stable ceramic shell. The wax is then melted out and recycled. The ceramic shell is fired at over 1,000 degrees Celsius to prepare for casting. Key quality factors include melt analysis, casting temperature, and shell temperature. Molten metal, up to 1,680 degrees Celsius, is poured into the shell. After cooling, the shell is removed, and the parts are separated, blasted, fettled, and possibly heat-treated. The raw part is then ready or further processed. Casting's precision complements forging, where brute force shapes metal. The brass forging process begins with mold design and bar cutting using 15 CNC saws for diameters from 12 to 85 millimeters. Cut pieces undergo graphite coating before hot forging with 16 presses ranging from 200 to 550 tons. Forged parts are trimmed using robotic and semi-automatic cells. Sandblasting follows for surface cleaning. Finally, parts receive custom mechanical machining and finishing. Campris forges 13,000 tons of brass yearly, from 5 grams to 6 kilograms. The lapping process begins by loading the ball valve and sealing seats from above. The machine simultaneously laps the ball and both seats, ensuring precise contact surfaces. Each drive shaft operates independently with continuously adjustable speed and pressure. An integrated metering device steadily dispenses the lapping mixture. The sealing seat movement stroke is adjustable for optimal surface contact. Used compound is collected in a drip container. A timer controls the cycle, and the process automatically stops when complete, ensuring efficiency and consistent quality. Beyond forging, bending and forming create diverse profiles for construction. The section bending machine cold bends various profiles such as pipes, beams, and angles using 3 rolls with fixed axes and 1 adjustable roll. The adjustable roll, power actuated, moves to apply pressure on the workpiece. As the material passes through the rotating rolls, it gradually forms into a precise curve. The bending process using the MC150 Nargisa section bending machine involves several key steps depending on the profile and material. To bend a flat bar on its flat side, rollers number 3 and 5 are placed and adjusted, followed by washer number 2 and nut number 1. The top handle is lowered to contact the material, and the machine is moved side to side without applying load until the desired radius is achieved. For edge bending, the roller gap is adjusted accordingly. When bending square or rectangular profiles, roller flour is used on the side and roller 5 with a washer and nut is fitted. The nut is tightened by hand. For round bars, the same roller setup as square bars is used. In all cases, side corrector rollers help straighten the profile. To bend U or T profiles, specific roller arrangements are used. For T profiles, roller 5 with shoulder and roller 3 with round edge are positioned inward. Stainless steel, brass, or aluminum require special nylon rollers to avoid contamination. For round pipes, tempered steel rollers matched precisely to the pipe size are used. The machine can also tilt to assist operation in confined spaces, or with Larid II. To perform a punching operation on the Nargisa MX700 hydraulic punching machine, begin by inserting the die into the lower base holder and securing it with a key. Next, attach the punch to the corresponding nut on the piston rod and tighten it firmly. To center the punch, lower the piston in manual mode, raising the die holder until the punch aligns with the die's hole. Center the base relative to the punch and secure it to the table with screws. Adjust the lower limit switch in manual mode so the punch penetrates only 2 millimeters into the die to prevent damage. Set the side stops to the desired position for accurate material placement. Lubricate the punch and die every 200 cycles to extend tool life. Ensure the punch diameter exceeds the sheet thickness to avoid breakage. Select an appropriate punch plate based on the punch size to enhance extraction and prevent deformation. For angle punching, adjust the upper limit switch so the punch's cutting edge clears the stripper plate. The angle punching tool allows close proximity to the angle's wall. For cutting 90-degree notches, use the stripper die, adjusting side stops independently to achieve cuts up to 150 millimeters. Folding operations use tooling with two V-slots, a 56 millimeter slot for 6 to 15 millimeters thick plates, and a 26 mm slot for 0.5 to 5 mm sheets. For larger folds up to 300 mm, use adjustable dies with varying openings for 0.5 to 20 mm thicknesses, with larger radii for thicker plates and smaller for thinner ones. Adjust the folding angle via the machine's stroke end. Pipe notching is streamlined with dedicated tooling, completing the process in 2 cycles for welding-ready pipes. Vertical cutting dies handle sheets and flat bars from 0.5 to 20 millimeters thick, up to 200 millimeters wide, requiring precise adjustment of clamping screws. For ventilation grids, align the punch wedge with the die, centering it for clean cuts, repeating as needed for the grid size. To create arrow shapes from hollow pipes, set the upper limit switch, lower the die without full compression, and center the pipe using side guides. Round bar cutting tools process bars up to 35 millimeters in diameter. Fence turnstile tooling flattens and cuts tubes in 1 cycle, with a 2nd cycle for punching holes. Switch to automatic mode for operation, where the piston descends and returns automatically. Set the upper and lower limit switches for precise movement. The parts counter-track cycles. In manual mode, the piston only descends, aiding tool setup. The safety device allows operation without the protection screen when the red light is on. Otherwise, the screen must be lowered. The MX700's adaptability enables custom tooling attachment using a nut and adapter, supporting diverse applications. From shaping to machining, precision defines the next stage. At Frigatech SRL, the mechanical processing begins with in-house design and proprietary tool development. Raw materials are stored in an automated warehouse, ensuring efficient supply. CNC cutting machines then prepare blanks for machining. Depending on part complexity, production uses bar transfer machines, sliding or fixed-head lathes, and multi-spindle turning machines from Index, Tornos, and Bafoli. CNC transfer machines with up to 12 positions carry out precision operations. Machining centers like New Hampshire 4,000 handle complex parts. After machining, parts undergo washing and quality checks. Selected products are tested, deburred, and assembled. Logistics and packaging complete the process, readying parts for delivery. The ProTurn RLX 780 performs metal turning by rotating the workpiece up to 1,300 revolutions per minute, while the cutting tool, controlled manually and via CNC through the Pro RLX interface, moves along the X and Z axes. The operator can perform facing, turning, grooving, and threading with precision, ideal for short runs or custom parts. Each day begins with a task review with the trainer. The trainee machines components for a can-end assembly using CNC turning and milling. In the CNC turning area, cylindrical parts like shafts are produced. Then, in the milling area, square or round parts are machined with holes and threads. Raw metal plates are cut to size in the cutting center. Additional steps include additive manufacturing in the 3D printing room, surface preparation using a grinding machine and planer to remove forging skin, revealing the copper. All these steps are part of the trainee's practical experience as a cutting machine operator. The 5-ax Banner GT5-2G is built for demanding 5-axis machining in heavy-duty applications. With clamping forces of up to 50 kilonewtons, it ensures rock-solid stability during even the toughest cutting operations. A 40mm corner milling cutter runs at 200 meters per minute with a feed rate of 13 millimeters per minute and a depth of cut of 2.2 millimeters. On aluminum parts, a 32mm cutter operates at cutting speeds up to 420 meters per minute. A 31mm solid carbide drill handles precise drilling at 100 meters per minute. Finishing is performed using a solid carbide end mill at 240 meters per minute and over 2700 millimeters per minute feed rate. Martinrea International focuses on developing lightweight structures and propulsion systems to reduce vehicle weight and fuel consumption. Their expertise includes metal forming and aluminum casting for automotive components. The company embraces flexible manufacturing, providing just-in-time solutions and vertical integration for industries like automotive, aerospace, and agriculture. Martinrea prioritizes teamwork, evolution, and commitment, consistently facing challenges and advancing technology to meet customer needs globally. They work closely with clients to engineer innovative solutions, ensuring high-quality products and services in every process. Martinrea specializes in the production of lightweight structures using steel, aluminum, or composite materials, including chassis, body-in-white solutions, and battery trays. Their advanced propulsion systems encompass engine, transmission, thermal, and fluid products, optimized for performance. The company employs flexible manufacturing techniques, offering capabilities in complex welding, blasting, painting, and just-in-time production to deliver high-quality, efficient solutions to customers from start to finish. The new CAT 320, GC 320, VA 323 excavators are assembled in the U.S. through robotic welding, precision machining, painting, and final assembly. Key components like the boom, cab, and hydraulic system are installed in sequence. Each machine undergoes rigorous testing to ensure optimal performance and durability before delivery. The CAT D8T rebuild process begins with complete disassembly of the machine. All components are inspected, and worn parts are measured according to CAT standards. Reusable parts are retained, while those not meeting criteria are replaced with genuine new ones. Critical design updates are applied where necessary. After cleaning each component to CAT cleanliness standards, the machine is reassembled and performance tested to restore like-new condition. Around 65% of parts are reused, enhancing sustainability. Finally, the machine is repainted and undergoes final inspections, resulting in a fully restored CAT D8T with extended life and updated functionality at a significantly lower cost than buying new. Valves and cables are critical components, requiring specialized processes. The manufacturing process of Wonkwang valves begins with material stocking, where raw metal is stored and managed. Meanwhile, sand preparation and injection are carried out to create molds. An automatic molding machine shapes the outer mold, while cores are separately produced to form the internal cavities. The molds are then cleaned and casting sand is injected to ensure a precise finish. The core and mold are combined and transferred to the smelting furnace area. In the smelting phase, metal is melted and then poured into the mold cavities. Once solidified, sand robbing removes the surrounding mold material. The castings are sent for post-treatment, including cooling, cleaning, and surface preparation. The components then move to the standby fabricating area. Machining starts with CNC lathes, Puma 400, 300, 280, 222 and universal lathes to perform turning operations. Drilling is done using upright drills and drilling machines. Chip removal ensures clean surfaces for assembly. The processed parts enter the assembly process, where all components are precisely fit. A hydrostatic test follows, using high-pressure testers up to 80 tons to check for leaks and structural integrity. Pneumatic testing and final inspection ensure product quality. Then, the hand wheel is assembled, and tagging for identification is completed. The valve proceeds through washing, first and second painting stages, via trolley coating lines, and is cured in an infrared oven. A final test confirms readiness for delivery. In the AFWL 110 cable shielding line, the forming and welding process begins with precise feeding and alignment of metallic. The SLT 400 to 0 degrees laser cross welding system performs fully automated cutting, positioning, and butt welding of tapes, with thicknesses from 0.05 millimeters to 3.00 millimeters and widths up to 400 millimeters. Using high-power fiber lasers, 500W, 1500W, it achieves narrow, deep penetration welds without filler material. The process yields high-strength, repeatable seams, eliminates pre-cleaning, and reduces downtime, ensuring continuous, high-efficiency production for cable shielding applications. The production process of TES generators begins in the design department, where each project is tailored to customer requirements. Engineers apply advanced tools such as RM Expert, Maxwell, and FEA to ensure precise electromagnetic calculations. Key components are optimized for durability using Autodesk Inventor and ANSYS Mechanical, guaranteeing performance and compliance with industry standards. The lamination phase involves stamping steel sheets to form the stator and rotor cores. These laminations are carefully stacked and welded to minimize energy losses and meet exact tolerances. Simultaneously, the tool-making team manufactures specialized jigs and fixtures required for accurate production. During the machining stage, various parts such as shafts, housings, and flanges are precisely machined. These components undergo strict machining checkups to ensure dimensional accuracy and surface quality. Next, the winding and assembly stage involves inserting coils, performing electrical connections, and impregnating the windings with resin to enhance insulation and mechanical strength. Final assembly integrates all components into a complete machine. Each generator is tested in the test field using advanced equipment to verify electrical performance, mechanical balance, and noise levels. Results are documented for quality assurance and certification compliance. After successful testing, Machines undergo paintwork to protect against corrosion and environmental factors. Finally, in the dispatch stage, generators are packaged and prepared for delivery, ensuring safe transport. This process, supported by in-house capabilities and stringent quality control, ensures high-performance generators tailored to customer needs and global standards. The production begins with the stator, where conductors are inserted and soldered into place using ergonomic winding stations. Solder joints are ultrasonically tested, and the stator is assembled further. Meanwhile, the stator core is created by stacking over 100,000 steel laminations into a large welded package. It is then rotated horizontally for bar insertion. After bar positioning and insulation, the assembly undergoes vacuum resin impregnation to eliminate air pockets and ensure durability. The rotor shaft is precision machined in several steps, followed by a quality inspection. Its winding cap is thermally expanded and mounted. A final roundness and dimensional check is performed on a lathe. The stator and rotor are then assembled in a process called the marriage. Before shipment, the complete generator undergoes extensive testing in Siemens Energy's high-tech control center. This ensures reliable operation under real conditions and secures long-term performance in power plants or grid stabilization systems. The rewinding process of a large motor at Koffler begins with disassembling and inspecting the motor to identify faults. The old windings are carefully removed from the stator, and the core is cleaned thoroughly. New coils are then precisely wound and inserted into the stator slots following exact specifications. These coils are connected, insulated, and securely tied in place. After rewinding, the stator is coated with a blue epoxy anti-corona paint to protect against electrical discharge and improve durability. Any excess epoxy is removed to maintain a clean finish. The rotor and other rotating components undergo dynamic balancing to reduce vibration and ensure smooth operation. This step is crucial for motor performance and longevity. Once reassembled, the motor is mounted on a custom-built test stand. It is then subjected to a series of electrical and mechanical tests using advanced diagnostic equipment to verify its functionality and reliability. KOFF LER's high standards and use of top-quality materials guarantee a fast and efficient remanufacturing process, restoring the motor to optimal working condition. The electric motor restoration process begins with a comprehensive disassembly. The motor is first carefully lifted using an overhead crane and positioned on a secure workbench. The end bells are removed using impact wrenches and pullers, followed by the detachment of the rotor from the stator. Technicians measure and record shaft runout and housing bore dimensions for alignment references. All fasteners and shims are labeled and stored systematically for reassembly. Once disassembled, the rotor, stator, housing, and covers are thoroughly cleaned. The stator and rotor are initially degraded using high-pressure steam washers at approximately 180 degrees Fahrenheit to remove oil, dirt, and carbon buildup. For more stubborn contaminants, an alkaline soak or solvent bath is used. Compressed air at 90 to 100 psi is then applied to remove residual moisture and particles. Bearing housings and shaft ends are cleaned and checked for scoring or deformation using micrometers and bore gauges. After cleaning, visual inspections are performed to detect cracks, hot spots, or mechanical damage. The stator windings are tested with a high potential test, and insulation resistance is measured with a Megger tester. If the windings fail, the stator is rewound. The old copper wire is removed, and new coils are wound according to the original design. The rewound stator is subjected to a vacuum pressure impregnation cycle using epoxylite 478 varnish. The VPI system operates under the vacuum of ensuring full penetration of varnish into windings. The stator is then baked at 135 degrees Celsius for several hours to cure the varnish. While the stator cures, the rotor is inspected for bent shafts, cracked bars, or out-of-balance conditions. Rotors above 15 HP or 3,600 RPM are dynamically balanced using a 5,000 lb capacity machine. Balance corrections are made by drilling or adding weights. Shafts are polished or machined on a lathe to achieve a surface finish of 16 to 32 micro in and correct dimensions. Reassembly begins by installing new bearings, typically double-shielded or open type depending on application. Bearings are heated to approximately 230 degrees Fahrenheit using an induction heater before being mounted to prevent shaft damage. The rotor is carefully aligned and inserted into the stator using hoists and alignment tools to avoid contact damage. End bells are mounted, and all components are torqued to manufacturer specifications. Rotor-stator air gap is measured to confirm proper alignment. Once reassembled, the motor undergoes electrical testing, including surge, insulation resistance, and high voltage withstand tests. If required, it is connected to a dynamometer for full load performance validation. After passing all tests, the motor is painted, labeled. The rotor removal process begins by aligning a custom 20-foot steel guide tube with the generator. Two 50-ton cranes carefully lift and support the 45,000 lb rotor. Using the guide tube and a hydraulic system, the rotor is slowly floated out of the 32 megawatts generator stator, maintaining a clearance of only 3/4 inch. Enerpac's hydraulically actuated system ensures precise control and reduces manual labor and time during removal. The maintenance process of the 16.5 megawatts generator begins with pulling out the rotor. Both the rotor and stator are thoroughly cleaned to remove any dust or contaminants. Bearings are then inspected to ensure proper function. A remaining life assessment is performed to evaluate the condition of critical components. Technicians check the wedges for tightness and integrity. A bump test is conducted on the stator end windings to detect any looseness or vibration issues. Finally, the rotor and stator are revarnished to restore insulation and protect against future degradation. The 6 kV 3 pH 50 Hz to 500 kW slip ring motor was restarted under 800 volts at Pascal Delafontaine Electromechanique. Rotor rings were short-circuited through fixed resistors to control inrush current, ensuring safe and smooth acceleration during post-revision workshop tests for cement industry application. The 6 kilovolts, 3-phase, 2,200 kilowatts, 1,000 revolutions per minute slip ring motor for the cement ball mill is started using an AOIP liquid resistance starter with a star contactor on the rotor circuit. At startup, resistance is inserted into the rotor to limit inrush current and provide smooth torque. As the motor accelerates, the resistance is gradually reduced in steps by the AOIP controller. Once full speed is reached, the rotor circuit is short-circuited via the star contactor. The motor then drives the cement ball mill through a planetary gearbox, ensuring stable and efficient operation. The 3,000 kilowatt slip ring motor is mounted on the test bed and connected to the test system. After initiating startup, the motor accelerates steadily for about 90 seconds, reaching its rated speed of 993 revolutions per minute. During this process, electrical parameters and vibration levels are monitored to ensure smooth operation and validate motor performance. Cables are connected to the 1.7 megawatts electric motor, and engineers inspect all components to ensure proper setup. Mounted in foot design IMB3, the motor is explosion-proof and air-cooled via a tube jacket heat exchanger. After confirming alignment, power is supplied gradually using a 6 kilovolts inverter on the Berlin test bench. The squirrel cage rotor begins turning, reaching 1,486 revolutions per minute under close monitoring. Internal fans circulate air to maintain temperature, while external fans dissipate heat. Performance and vibration data are collected throughout the startup phase to confirm system integrity before operational deployment. Three compact squirrel cage motors, each rated at 1,700 kilowatts and 6,600 volts, drive mineshaft ventilation fans in a copper mine. Using frequency converters, speed is precisely controlled to regulate airflow. The fan wheel is mounted directly onto the motor shaft. The drive end bearing supports the fan's weight, while the non-drive end bearing in O setup handles axial forces. The motors use grease-lubricated roller bearings designed for 100,000 hours of operation. A totally enclosed IC411 cooling system ensures reliable heat dissipation. Electrical leads exit through the barrel-shaped housing to external terminal boxes, meeting space constraints and enhancing maintainability in the underground environment. Technicians use Parker interfaces and follow OEM specifications to fully run test the servo motor. The process involves connecting the motor to testing equipment, checking speed, torque, and feedback signals, and verifying all functions to ensure the motor meets performance and quality standards. The motor housing is first left free to spin as electricity is applied, bringing it to full speed. A brake is then gradually applied to the housing, slowing it down. This causes the rotor inside to spin up, allowing synchronization. Eventually, the rotor drives the load at full synchronous speed. Power is enabled, initiating the motor startup. Power builds up in the FTL drive as vibrations occur typical for aged systems. The drive continues spooling until completion. Once fully spun up, the 1,250 kilowatts motor is ready to engage the 12,000 kilograms wood chipper disc. Motors support critical infrastructure like ventilation systems. The 3.8 meters tunnel fan starts up remotely via the maintenance system, activating its heat and vibration sensors. Power flows through 1 kilometer of installed cabling. As it spins, the fan circulates fresh air and is ready to reverse if needed. Its energy-efficient design supports emergency operation at 300 degrees Celsius for up to 2 hours. The Mersey tunnel vent startup process begins with activating standby generators to ensure backup power. Control systems initiate the 32 jet fans and 44 ventilation fans to establish airflow. Data from 400 CCTV cameras and airflow sensors is monitored in the control room. If required, water pumps are engaged. MoJet fans deliver increased thrust for efficient ventilation. Sustainable energy infrastructure, like wind and aluminum, is shaping the future. Wind tower production begins with cutting, beveling, and polishing steel plates, followed by rolling into cylindrical sections. These sections undergo longitudinal and circular seam welding using 200T rotators. Afterward, the towers are sandblasted, painted, fitted with internal accessories, and finally packed for delivery. Steel plates up to 150 millimeters thick are bent into circular shapes and welded using DSAW for strong inner and outer seams. These heavy wall pipes are joined in the multi-section pipe fabrication process. The transition piece, including the barrel, deck plate, and girder, is assembled to secure the turbine structure. Legs are connected with X-braces to form the foundation. The lower jacket is constructed, then joined with the upper jacket and transition piece. After corrosion-resistant painting, the 94 meters 2,200T foundation is shipped. Located in British Columbia, the Kitimat aluminium smelter was established by the Aluminum Company of Canada in the 1950s and modernized by Rio Tinto in 2015. Powered entirely by hydroelectricity from the nearby Kamano powerhouse, the facility uses the Hall-Heroult process to produce aluminium. Refined alumina is injected into electrolytic reduction cells, where it dissolves in a molten cryolite bath. Carbon anodes conduct electricity into the bath, enabling a reaction that separates pure molten aluminium. This aluminium is siphoned and cast into ingots and slabs. With 384 pots in a continuous pot line, Kitimat produces high-quality metal efficiently and with reduced emissions, making it one of the most advanced and environmentally responsible smelters in the world. Rio Tinto modernized its Kitimat smelter by investing over $6 billion in advanced smelting technology, increasing production by 50%, reducing emissions by 50%, using clean hydroelectric power, and partnering with local communities and First Nations to create a sustainable aluminum future. In June 2015, Kitimat reached a historic milestone with the completion of its modernization project, beginning production of low-carbon aluminium using advanced AP40 technology, creating one of the world's most efficient, sustainable, and lowest-cost smelters, built on teamwork, innovation, and long-term vision. Experimental energy solutions push boundaries, sparking debate. The PMG Perpetuum Mobile Free Energy 8 kilowatts generator operates using a permanent magnet-based alternator, initially a small electric motor. Once spinning, the rotor's embedded magnets pass through copper windings in the stator, inducing an electric current without fuel. As the rotor gains speed, the system reaches self-sustaining operation, where the energy generated powers the motor and external loads. This closed-loop feedback is claimed to maintain continuous rotation, producing up to 8 kilowatts of electricity. The system features minimal noise and no emissions. Though called free energy, the setup relies on efficient energy conversion and reduced losses, not violating thermodynamics. It demonstrates an experimental approach to sustainable power using permanent magnets and smart design. Steam is admitted into the high-tension cylinder and expands to drive the piston forward. The exhaust steam then enters the larger low-pressure cylinder, where it expands further to complete the power stroke. Both pistons are connected to a shared crankshaft, rotating the 2.5-meter flywheel at 150 revolutions per minute. Valve timing is controlled by an eccentric disc and axis governor, ensuring synchronized steam distribution. A central oiler lubricates the moving parts, powered by belts and eccentrics. Exhaust steam is condensed below the machine via an injection condenser. The generator and exciter, belt-driven from the flywheel, produce 400 V at 160 kVA. Monitoring instruments track pressure, temperature, and speed during operation. The production process of Mannesmann H2-ready pipes begins with coil handling and strip preparation, followed by the strip accumulator and continuous welding system. The strip undergoes preforming and pre-shaping, then enters the HF welding zone. After welding, both internal and external weld beads are scraped off, and the weld is annealed. The pipe is then air-cooled with temperature measurement. Subsequently, pipe shaping and pipe string cutting are carried out, followed by pipe straightening. Quality checks are integrated, including pipe length measurement, ultrasonic pipe end testing, diameter and wall thickness measurement, longitudinal weld inspection, internal marking and labeling. In the finishing line, pipes pass through blasting units at both ends and internal blast compound removal. They are heated inductively for plastic coating, followed by powder application with primer/adhesive, hose extrusion, asterisk, and water cooling. Layer thickness measurement and inkjet marking complete the coating process. The pipes are then subject to pipe end finishing, internal checking, protective cap attachment, and final quality assurance. For transportation, pipes are handled via pipe transport trolleys, gantry cranes, and railcar loading systems. On-site, 1,900 pipes were GRP wrapped and installed using horizontal directional drilling over 14 sections across a 9 km route. The production of the 6,500-ton straightening press begins with advanced design, structural calculations, and FEM-based simulations to ensure mechanical stability. Key components, including the 270-ton upper press beam, are cast in-house at Simplecamp Gießerei. After cooling, the beam undergoes fettling and final machining, with high-precision tools on large portal milling machines. The 252-ton machined beam is then transported and assembled. The complete plant is installed and commissioned over the course of a year. In operation, the press uses a servo-hydraulic drive system with direct position measurement for force and position-dependent control. One or more straightening rams apply uniform pressure across the press width. Sheet metal up to 300 mm thick and 600 degrees Celsius can be cold or hot straightened. Roller tables automate loading, alignment, and unloading. Parameters such as press force and speed are monitored and controlled automatically. The system ensures highly accurate, efficient, and repeatable straightening processes. Laser welding of ductile cast iron components begins with non-destructive testing to locate surface cracks. Detected defects are fully removed via grinding to prevent future failure. The weld zone is then inspected again to ensure no remaining flaws. Using mobile robots, the laser beam melts the base material, while metallic powder is simultaneously injected into the melt pool. This enables deposition rates of up to 0.2 square meters per hour, with layer thicknesses between 0.6 to 0.8 millimeters. The process generates minimal heat input, reducing thermal distortion and eliminating the need for preheating. Robotic guidance ensures consistent weld quality, even on complex geometries or in difficult positions. The mobile laser unit, integrated with a powder feeder and protective housing, allows flexible operation across large components in different locations. The entire process is monitored in real time using special optics and cameras, ensuring precision and operator safety. The robotic sawing process starts by securely clamping the casting in place. Depending on the setup, maneuvers the saw blade around the stationary part. Using pre-programmed paths and sensor feedback, the robot precisely cuts gates and risers, even on complex geometries. This automated approach enhances safety, ensures consistent cut quality, and significantly reduces cycle time. It also minimizes operator fatigue and variability, making the process ideal repetitive degating tasks in modern foundries. Simple Camp Foundry is one of the world's largest hand-mold foundries, specializing in massive cast components weighing up to 320 tons. With Zeiss ATOS, the foundry utilizes advanced 3D scanning technology to perform fast, full-surface measurements, ensuring precision, quality control, and efficient digital inspection processes. Trainees at Simple Camp Foundry combine theory with hands-on practice daily. Trainees prepare sand molds, apply coating to molds, remove castings, and grind finished parts. They monitor each step carefully, ensuring quality and precision throughout the casting process in the Simple Camp Foundry workshop.